Hello everyone, welcome to our Projects and Seminars course, Hands-on Acceleration on Heterogeneous Computing Systems, or P&S Heterogeneous Systems for short. My name is Juan Gómez Luna. I'm a senior researcher in the Safari Research Group at ETH Zürich, and today I'm going to introduce this course, and I'm also going to introduce our research group and the course logistics. You can find the description of this course in the course catalog of ETH Zürich, and if you take a closer look at the objective, you will find the motivation for this course, which is the difficulty of scaling the performance and energy efficiency of CPUs. This affects very important workloads like machine learning and artificial intelligence, but also other workloads like bioinformatics, graph processing, medical imaging, and many more. And in order to solve these difficulties, there have appeared, and we use more and more these days, heterogeneous devices, like, for example, GPUs that have been key to the rise of machine learning and artificial intelligence and are going to be a key content of this course and how to program them, but also other types of heterogeneous devices, like, for example, FPGAs and accelerators like tensor processing units and other neural network accelerators that it's common to find these days in our heterogeneous systems. Or near data processing architectures that consist of placing some sort of compute capability near or inside the memory itself or the storage. But there are still many challenges to tackle in order to enable efficient heterogeneous systems, and this is why a course like this makes sense. But we are going to start simple. We are going to start with the taxonomy of computers from Mike Flynn, written in 1966, that divides the classes of computers into four. The first one is single instruction, single data. This is similar to a sequential processor where one instruction operates on a data element at a time. The second class in this taxonomy is single instruction, multiple data, where one single instruction operates on multiple data elements at the same time. There are two classic examples here that are the array processor and the vector processor. The most popular type of SIMD processor these days are GPUs, and they have characteristics of both array and vector processors. We are going to cover GPUs with a lot of detail in this course, and today we will start talking about SIMD extensions in existing CPUs. The third type are MISD, multiple instructions operate on a single data element. The closest form of MISD processor that we can find, or the closest form of processor that we can find closest to MISD is the systolic arrays. We will briefly mention systolic arrays as well in today's lecture. And finally, MIMD, multiple instructions operate on multiple data elements. We have multiple instruction streams as we can have in multiprocessors or multi-thread processors. But let's start talking about SIMD processors, and in particular, let's give this example of the SIMD ISA extensions that we find in most CPUs these days. The idea is to have a single instruction operating on multiple pieces of data at a time, and this is something pretty useful for some applications, for example, graphics or image processing, where we typically operate on pixels of the image or pixels of a graphic. We perform the same operation on all the pixels. We can make this more efficient, we can make this faster, and we can operate on multiple of these pixels at the same time. So the idea is to perform short arithmetic operations, also called pack arithmetic, using the several of these short arithmetic operations using the existing ALUs. For example, we can add 4 8-bit numbers, but to do so, we need to modify our ALU to eliminate carries between 8-bit values. For example, we need to eliminate the carry between bit 7 and bit 8, and between bit 15 and bit 16. And this way, we will obtain in the same operation 4 additions, as we can see in this slide. The first, if not the first, the most popular or the first one to become a very popular SIMT extension in CPUs were the MMX operations that appeared in the 90s. The idea is to operate on multimedia graphics workloads in a way that we can take advantage of the existing ALUs by operating on multiple data elements at the same time. And multiple data elements might be 8-bit bytes, or 4 16-bit words, or 2 32-bit double words, or 1 64-bit quad word. If you want to learn more about it, I would recommend you the original paper published in IEEE Micro in 1996. But we are going to see a little bit more detail. We are going to see an example where the goal is to overlay the human image X on top of the background image Y. So here on the left, we have this image X that has the image of a woman on top of a blue background, and we want to replace the blue background with a blossom background in order to obtain a new image, the one that you see at the right-hand side. If we want to, we have to perform this computation on a sequential CPU. What we are going to do is going one by one over all the pixels of the image, and for every single pixel we compare it to blue. If it's blue, we replace it in the new image with the corresponding pixel from the image Y, from the blossom background. And if it's not blue, that means that it belongs to the woman. So we place in the output image the corresponding pixel in the woman's image. As you can see, the code for this operation on a CPU is pretty simple, pretty straightforward. We are going to need a slightly more complex program if we want to do this on a SIMD processor or on the MMX extensions. The very first thing that we obtain is a bit mask that distinguishes between those pixels in image X that belong to the woman and those pixels that belong to the background. What we do is comparing the pixels from the image X that are stored here in this register MM3, we compare them to register MM1 that has all elements equal to blue. So if one particular pixel in MM3 is blue, then in the output, we are going to have all ones. If it's not blue, we are going to have all zeros. And now let's see in the next slide how we use this bit mask. We are going to apply these bit masks to both the blossom image and the woman's image. So here on the left, we have the blossom image. All the pixels or pixels from the blossom image are here in MM4, and we AND this blossom image with the bit mask that we calculated before in order to obtain this output MM4 that has pixels from the blossom image and also pixels equal to 0. And then on the other hand, we do something similar with the woman's image, but in this case we invert the bit mask because before performing the AND operation. So here we have in MM3 pixels coming from image X. Some of them belong to the woman, others belong to the blue background. We perform the AND operation here and we obtain this output in MM1. Now, if you compare MM1 and MM4, you see that we can clearly OR them and have the result in this output array MM4, where we obtain already pixels from the final image with the woman on top of the blossom background. So if you want to write this code, here you have this instruction is relatively simple, relatively packed. Remember, the first thing we need is comparing to the register containing all elements equal to blue in order to generate the mask. Then we have this pack AND for the blossom image. We have this pack AND NOT for the woman's image, and finally the OR operation to merge, to combine the pixels coming from image X coming from image Y and put them together in the final image. So this is just a very simple example of the type of computation that we can have in heterogeneous systems. And it's more and more frequent that we have not only SIMD extensions as MMX, but also many more complex heterogeneous devices in the same system, in the same package, or even in the same chip. And these devices can be CPU cores with their cache hierarchy, they can be GPU cores, or they can be reconfigurable fabric like FPGAs, or also other types of accelerators. I mentioned neural network accelerators, for example, in the beginning of the lecture. All these processors, all these devices have access to some external memory, typically DRAM through a DRAM controller, and they can also share data using the shared levels of cache, and in some cases we also find coherent interconnects to make sure that all these processors here always access updated values of the variables. We are going to introduce these coherent interconnects also in this lecture, and we will talk about them. We will talk about them in later lectures as well. So let's first of all define what are the goals of this P&S course. This P&S on heterogeneous systems, you will introduce, or you will be introduced to the need for heterogeneity in current computing systems in order to achieve high performance and energy efficiency. You will get familiar with some of the different heterogeneous devices that are available in computing systems. You will learn workload distribution and parallelization strategies that leverage heterogeneous systems, and you will work hands-on, analyzing workloads, programming heterogeneous architectures, proposing scheduling and loading mechanisms, etc. And at the end of the course, you will hopefully be familiar with many heterogeneous devices. For example, this NVIDIA A100 GPU from 2020, which is the most powerful GPU from NVIDIA these days. And this, as you see on the screen, contains 108 cores and 40 megabytes of L2 cache. And if we take a closer look at this GPU, we can see these in the image, one GPU core or a streaming multiprocessor, or SM in NVIDIA terminology. And if you check the different blocks that compose this A100 core, you will see that it's also heterogeneous by itself. It has integer 32 units, it has integer 32-bit floating point units, 32-bit floating point unit, 64-bit floating point unit, and also other specialized processing elements that are called tensor cores, that are specialized for deep learning. We will talk about them in a later lecture. And also for deep learning, we have seen appear many new devices and many new accelerators due to the importance of machine learning and artificial intelligence these days. And a very good example is this Cerebras wafer scale engine from 2019. That is the largest ML accelerator chip. Actually, it's not even a chip, it's an entire wafer composed of multiple tiles with memory and with processing elements to be super fast and super energy efficient for machine learning workloads. And more recently, in 2021, Cerebras released the new version of the wafer scale engine, the wafer scale engine 2. If you want to learn about this fascinating accelerator, I would definitely recommend you the talk that one of the founders, Sean Lee, gave in our group very recently, and when he described many inner details of the design, the fabrication of this accelerator. And it's not the only important accelerator for machine learning and for neural networks. Since 2016, we have the Google TPU Tensor Processing Unit. It was presented in ISCA 2017, and we have already seen 4 successive generations of this Google TPU. The second generation was released in 2017, in 2019 the third generation, and in 2019 also the 4th generation. And each of these generations has been more and more powerful, more teraflops, more memory as well. But in the end, all of them are conceptually the same. They are a modern systolic array, and here you can see a nice schematic of this TPU with this matrix multiply unit here on the right-hand side. That is a systolic array that performs matrix multiplication very efficiently by combining values coming from these FIFO of weights and also the input data, input feature maps coming from these other buffers here. And also you can see the rest of the components with interfaces to access external DRAM and also being accessed from the host using a PCI Express bus. So this is one more example of a heterogeneous device, but even inside the same chip, we can also find pretty interesting examples, like for example, this Xilinx Versal ACAP from 2020 that has different types of devices inside the same chip, because the designers know that it's important to have the right devices for the right workloads. And that's why if you take a look at the internals of this Intel Versal, you will see that there are some scalar engines, like for example, ARM dual core. There are two types of cores here. There are also adaptable engines that are completely configurable and can also be used to create a custom memory hierarchy. This part here is the most similar to a reconfigurable fabric or an FPGA. And here on the right-hand side, we have these intelligent engines that are designed for machine learning and artificial intelligence, and are essentially like a SIMT processor. All of them connected via a network on chip with access to an external memory, and also you also find other different components here, like the memory controllers. I mentioned before another type of heterogeneous device is near data processing. Near data processing or processing in memory. The key idea is placing computation near where the data resides, for example, inside the DRAM memory chips. And this is what UPMEM, a French startup, did since 2019, where they are commercializing these UPMEM DIMMs, PIM-enabled DIMMs that contain PIM chips. And inside each of these PIM chips, we have memory arrays, DRAM memory arrays, and small processors called DRAM processing units, or DPUs. These are general purpose processors that can be used for many different applications. And it's really fascinating architecture, and also very related to our research work. And we are talking about this architecture and about other processing in memory architecture in our processing in memory course that I would definitely recommend to all of you. Another example of processing in memory architecture is the Samsung AX DIMM that it's a DIMM-based PIM solution. Essentially here, what we do is in DRAM DIMMs, we can place some sort of processing capabilities. In this case, in this paper, they demonstrated this system by including an FPGA on the DIMM and configuring or customizing this FPGA for our recommendation system. And they showed pretty interesting results. We will talk about this AX DIMM. We talk about this AX DIMM as well in our processing in memory course. And Samsung is not the only major DRAM vendor that is working on processing in memory. Very recently, actually a couple of weeks ago, SK Hynix, another major DRAM vendor, announced their Accelerator-in-Memory. And here, what they do is placing processing elements inside the GDDR6 memory, also, and same as the Samsung architectures targeted at machine learning workloads. Another thing is, okay, you have many different accelerators in the system, many different types of general purpose processors, CPUs and GPUs in your system, but now connecting them is not as easy. And that's why there has also been a lot of effort in the academia and in the industry to enable ways of connecting the different heterogeneous devices in a way that is seamless, that is high throughput, and that is low latency. Because traditionally, what we had to do is moving the data moving the data in chunks from the CPU memory, from the main memory to the memory of the accelerator, and after that start the computation on the accelerator side. And all this communication was responsibility of the programmer that needs to decide when to move something from here to there in order for the different heterogeneous devices to have access to the most recent values of each variable. So fortunately, industry has started, several industry consortiums have started to develop interfaces that are coherent. The coherent accelerator processor interface, CAPI, is one of these examples. OpenCAPI is a larger consortium that was started by IBM, but also encompasses many other big actors in the industry. And this coherent accelerator processor interface allows the seamless integration of an accelerator, for example, an FPGA, into a CPU system, and for the CPU to have direct access to the memory of the FPGA or vice versa. And it's on not only this OpenCAPI, we have also seen similar ideas in Intel devices as well. For example, this Intel Harp that integrates an Intel Xeon processor and an FPGA in the same package. And also they have this fine grain, so they are tightly integrated and fine-grained, so they are designed for fine-grained collaboration between the CPU side and the FPGA side. And another very good example is this Compute Express Link, another open industry standard interconnect offering high bandwidth, low latency connectivity between the host processor and the devices. And it has, let's say, different ways of being used with accelerators with their own memory and with memory buffers. We will talk about this CXL also in a later lecture as well. So key takeaways of this course and how you will feel after you finish this course. This P&S is aimed at improving your knowledge in computer architecture and heterogeneous systems, your technical skills in programming heterogeneous architectures, your critical thinking and analysis. You will interact with a nice group of researchers, with the Safari research group, and this way you will also become familiar with key research directions. And in the end, you will also improve your technical presentation skills because you will have to present your project in front of our group. The key goal of the course, again, is to learn how to take advantage of existing heterogeneous devices by programming them, analyzing workloads, proposing offloading, scheduling techniques, etc. And prerequisites of this course, you probably know them. It's important to have a relatively good background in digital design and computer architecture. If you need to brush up in any of the contents of these courses, I can recommend you Professor Mudlu's course on digital design and computer architecture. And you can find a link to the Spring 2021 edition and to the current Spring 2022 edition that Professor Mudlu is delivering these days. It's necessary for this course to have familiarity with C and C++ programming, and if you also have familiarity with FPGA implementation or GPU programming, that's even better. And what we expect from you is that you have an interest in computer architectures and computing paradigms, discovering why things work or do not work and solve the problems, and making systems efficient and usable. Let me very briefly introduce the Safari Research Group, and I'm going to start with Professor Mudlu, who is the leader of this group. He is at ETH Zurich since September 2015, but before that he was at Carnegie Mellon University and also in several companies. If you want to learn about him, about his research, here you have links to his website and also his email address in case you want to contact him. For many years, he has been doing research and teaching in computer architecture, computer systems, hardware security, bioinformatics. The rest of the team is me, Juan Gómez Luna. I'm as I said in the beginning, a senior researcher in the Safari Research Group. And there are 3 more supervisors in the course: Dr. Mohamed Alser, who works in bioinformatics, processing in memory, hardware acceleration; Dr. Beksat Salami, who also works in hardware acceleration with FPGAs; and Dr. Gagan Singh, who works in machine learning and hardware acceleration as well. You can learn more about us and about the research group in the Safari Research Group website. It's a very large group with more than 40 people, and we are very proud of what we are doing, our research, and we want to disseminate it as much as possible, not only with our research papers, but also with, for example, this Safari newsletter that we release from time to time. The most recent one is from December 2021. We also organize live seminars where people from our group and also from academia and from industry come and give very interesting lectures about the research. And the last one we had, I already mentioned a few slides ago, is this talk by Sean Lee, co-founder of Cerebras, where he talked about the wafer scale engine. Accelerators, processing in memory, computer architecture in general are the main topics of our interest and the main research lines in our group. As you can see, a summary of these research lines: computer architecture, hardware, software, co-design, bioinformatics, memory and storage, heterogeneous devices, processing in memory, and many more things. Essentially, all aspects of computing systems, from the architecture and the devices to the applications. Course requirements and expectations of these P&S on heterogeneous systems. Attendance is required for all meetings. Study the learning materials each student will carry out at a hands-on project, and we hope you participate, ask questions, read the relevant papers, and so on. We will help you with your project, and if your work is really good, it can even get published. You can access more information about the course in the course website, and we will also have Moodle Q&A in case you need it. For this first week, there are some required materials: this lecture on an introduction to SIMT processors and GPUs, and also an introduction to GPU and heterogeneous programming. We will start talking about all of this in our next lecture, but it's good for you to take already a look at these materials, because this way you will be more familiar and you will feel more comfortable in the next lecture. And there are also here some other recommended materials, like some relevant papers from our group. In the second meeting, we normally present the different hands-on projects we offer to the students, and after that, the students rate their preferences, and we have later one-to-one meetings to discuss their interests, their skills, and how suitable their background to the specific projects that they have voted for is. But it's important to study the learning materials in order to be already familiar with the heterogeneous systems before deciding about the project. In next meetings, we will talk about heterogeneous systems with a special focus on GPUs and GPU programming. But we will also have lectures about FPGAs, for example, and about other some of our recent research works. And at the very end of the course, after finishing the hands-on project, you'll have to present your work. If you want to know more or less about the structure of the course, I can recommend you to take a look at the website of the past semester of fall 2021, where you can find there all the lectures and all the materials, presentations, and so on. Okay, and before we finish, I would like to very briefly recap on what the heterogeneous systems are, recap on this taxonomy of computers by Mike Flynn, that we started the class with, and talk a little bit more about SIMT processors and GPU, which will be the main content of the next lecture. So remember, we have 4 classes of computers: SysD, SIMD, MISD, and MIMD. And I start in this course focusing on SIMD processors, that are those that allow us to execute, to operate on multiple data elements using a single instruction. We have seen this example of the human overlay, where we take pixels from one image X containing the image of a woman. We take pixels from one image Y containing a blossom background, and we combine them in order to create a new image that has the woman on top of the blossom background. The way of doing this computation, or one way to do this computation, could be sequentially, going one by one over all the pixels of the image. The way we explain here by using these MMX extensions allows us to operate on multiple pixels at the same time, and this way be more efficient and essentially faster. SIMD processors, in summary, operate with a single instruction on multiple data elements at a time, or in the same space, because this is this duality that we have in time of our space, as we are going to see in this slide and the next slide. Is what we call the time-space duality, that allows us to distinguish between array processors, that are processors where one instruction operates on multiple data elements at the same time using different spaces or different processing elements, and a vector processor where an instruction operates on multiple data elements in consecutive time steps using the same space, the same processing element. Here you see on the left-hand side, we have our first SIMD code, or it's this instruction stream with a load instruction, an addition, a multiplication, and a store operation. Here, what we are doing is using vector registers, that are these registers containing multiple elements that are going to be operated on by the same instruction. And the first thing that we do is loading data from memory, from this array A into the vector register. Then we add 1 to the vector register. Then we multiply 2 the contents, the individual elements in this vector element. We multiply them by 2. And finally, we store the results in the corresponding location in memory. How do we execute this on a SIMD processor? It depends on whether this is an array processor or a vector processor. In the case of the array processor, we have multiple processing elements. All of them are exactly the same, and all of them are able to execute different types of instructions. And this way, in the first cycle, we issue the vector load, this vector load instruction that is going to be mapped and is going to be executed on these 4 processing elements at the same time for the 4 elements that the vector register contains. In the next cycle, we issue the addition, then the multiplication, and then the store operation. So as you see, we have the same operation at the same time on different spaces, on different processing elements, but we have different operations in the same space at different times, as you see here. So this is the time from top to bottom and space from left to right. In a vector processor, we have different processing elements. Each of them are specialized. So if we want to execute a vector load, for example, we will have to issue 1 load of 1 element every cycle. And in the addition unit, we can do the same for the addition instruction. We will execute the addition first for element 0 in the vector register, then for element 1 in the vector register, and so on. And this way, we are creating kind of a pipeline of operations across the processing elements of the vector processor. As you can see, we have different operations at a time. As you see here in this particular cycle, we have a load, an add, a mul, and a store in the 4 different processing elements of different operations at the same time. And we have the same operation in the same space because these processing elements are specialized. And even though this classification and this distinction of array and vector processors might look like too simple and kind of obvious, this is the way we keep building SIMD processors these days. And actually, a very good example is the core of this A100 GPU, where remember we have different types of processing elements like these 32-bit integer, for 32-bit floating point, for 64-bit floating point, etc. But also we have multiple of these. So what that means is that we can operate on multiple 32-bit elements at a time, or 32-bit floating point elements at a time, and so on. So a GPU in the end combines some characteristics from the vector processor and characteristics from the array processor. And it's not the only computing paradigm that it incorporates, that GPUs incorporate into their architecture, fine-grained multi-threading as well, as we will start discussing in our next lecture. So these are relatively complex systems with a lot of potential in terms of energy consumption, and so in terms of energy efficiency and performance, but they also have disadvantages. And this is something that was already pointed out by Fisher many years ago in 1983 in this ISCA paper, where he says, to program a vector machine, the compiler or hand coder must make the data structures in the code fit nearly exactly the regular structure built into the hardware. If you look at the vector and the array processor that I just presented, or the A100 GPU, you will see that the structure of these devices, of these processors, is very regular. But the problem that we need to solve, and the data structures that we may need to use to solve our problem for your algorithm or application may not be so regular. And perfectly mapping the data structure onto the hardware is something really challenging. As Fisher said, that's hard to do in first place and just as hard to change. So one of the key challenges and one of the key weaknesses of vector processors and SIMT processors and even GPUs is the difficulty of programming them in an efficient manner. And this is why it's important to have one course on programming heterogeneous systems like this one. How are GPUs programmed these days? They are heterogeneous applications. So the GPUs are part of an heterogeneous system, and in this heterogeneous system, we are going to have a heterogeneous application running on it, and that means that we are going to keep using the GPU, but also CPU threads that run on a CPU in a way that serial or modestly parallel sections of the code or the application will keep running or continue running on the CPU, while massively parallel sections of code will run on the GPU, will run using blocks of threads. We will see what the blocks and the threads are in the next lecture. But yeah, that's essentially the structure of one of these heterogeneous programs. We will have some serial code or modestly parallel code running on the CPU. Then at some point, we will reach to a parallel section where we can operate on multiple data elements at the same time. And what we will do here is launching the GPU function, the function that runs on the GPU that is called parallel kernel or simply kernel. And here we define the number of threads that we are going to use on the GPU, and we group these threads into blocks in a similar way as you can see on the slide. When one kernel terminates, the controller returns to the CPU, some more serial code is executed on the CPU, and at some point, a new kernel may be launched for execution on the GPU. We will learn a lot of how to program GPUs in this course. We will learn about how to write GPU code, or in particular, we are going to work with the CUDA framework mostly. Here you have some sample simplified code. This is just a vector addition, how you would implement it using C code on a CPU, and how you would implement it using CUDA code. Notice that here we call global the kernel, the function that executes on the GPU. If you look at the body of this kernel, you see that it's essentially memory access and addition, and finally a store in the output array. See, the key difference between this CUDA code and the CPU code is in the CPU code. We are simply using an index, this index II, while in the GPU, we are using a thread index, an index that identifies each of the different threads that we are using in our program. And based on this thread index, we access different elements in memory and operate on them. So, as you see, this code is not really complex. We are going to see a little bit more complex codes in this course, but hopefully you will understand them all, and we will overcome this key disadvantage of vector processors and SIMT processors and GPUs. That is the difficulty of programming these systems. Hopefully, at the end of the course, you will be familiar with different heterogeneous computing systems and heterogeneous devices, even though we are going to have a main focus on GPUs and GPU programming, but that can also be the way of getting introduced into the heterogeneous computation. And hopefully as well, at the end of the course, you'll be able to write your own heterogeneous applications, such as the ones that you can find in this CHAI benchmark suite that features different collaboration patterns. We will talk about these collaboration patterns, about the CHAI benchmark suite in a future lecture. It's a benchmark suite containing heterogeneous workloads written in different programming languages like CUDA and OpenCL. And here you have a link to access the website, and from there you can also access the paper and the repository. This is all from my side today. Thank you very much for your attention. I hope you enjoyed this introduction to the course. In the next lecture, we are going to go into many more details about the architecture of SIMT processors and GPU. I hope to see you again here next Tuesday. Thank you very much for your attention. Have a nice day.